Hello and welcome to our lesson on domain and range. So domain and range are going to be features of a function that we should be able to identify, whether we're looking at a set of ordered pairs, a graph, or an equation for a function. We should be able to identify that function's domain and range. So if you recall from the last lesson, we said a function is going to be a relationship between two variables, and usually those variables are x's and y's. And for every x value, there's going to be one corresponding y value. Well, if we took all the x values and all the y values, assuming they corresponded, and created a function, we're going to call all of those x's the function's domain, and we're going to call all of those y's the function's range. So the domain of a function is going to include all x values for which that function is defined. And if we're going to be reading our domain from a graph, we're going to read from left to right, which should make sense. If we're trying to identify the x values that are encompassed on that graph, we're going to use the x-axis as the guide. And since it runs from left to right, we will read from left to right. So our domain is going to be made up of the leftmost x value to the rightmost x value. Okay, and then the range will be similar. So range is going to include all the y values for which the function is defined. And if we're going to try to identify those on a graph, we're going to use the y-axis as the guide. And so the y-axis is running up and down. And so we're going to go from the bottom of the graph to the top. What is the lowest y value? What is the highest y value? And that's what we're going to include in our range. So we're going to read from the bottom of the graph to the top to capture that lowest y value and highest y value in the range. Okay. Now once we've established the leftmost and rightmost x values, or the lowest and highest y values for that domain and range, there are a couple different ways that we can state these things. So domain and range can be stated using sets or using intervals. And it looks really sloppy. My penmanship's not, yeah. Technology. Okay. Intervals. There we go. So set notation, I'm going to give you a little generic version of it here. Set notation, and you don't need to write this, but it usually, here, let me go here, looks something like this, where you have this brace here, and you have, let's say we were looking at domain, we would put an X, and then this little bar, and then we would put a description here of what's going on with our X's. And if it was range, then you would have something similar, but it would be a Y in this little bar, and then again there'd be a description in here. And you would read this as all x's such that, I don't know, the description could be the x's are less than 2, or the x's are bigger than 5, or whatever it is. But I'm not so concerned with the formality of the set notation. What I want is for you to be able to capture the description mathematically. So be able to tell me that the x's are greater than 2, or the y's are less than or equal to -4, or whatever the description is, okay? So if you've seen all of this stuff before, don't worry about it. I don't want to be too formal here. I just want you to be able to succinctly describe mathematically what's happening with our domain and range. So our set notation is going to be a little more informal. We're really just going to be looking for an inequality to describe what's happening. It won't always be possible, but majority of the time it will be. So an inequality would be a greater than, less than, greater than equal to, less than equal to. Or we can use an interval. In the interval notation, I think that's the more commonly used one, but it's got 4 components to it. So whether it's domain or range, we go from the smallest to the largest value in the set. And that should make sense for an interval, right? If I said, from what interval of time are we watching this video? And maybe you sat down at 11 and you're done at 11:30, whatever it is. So you would tell me when you started and when you stopped, okay? So that would be the same for domain and range. Where does my domain start? Where does it stop? What's the leftmost x value? What's the y-most? Or rightmost? And then if it's range, what's the lowest y value? What's the highest? The start to the stop, okay? So we always have our smallest value here. And then we have our largest value here. And that could be the leftmost or lowest, depending on if it's domain or range, and it could be the rightmost or highest, again, depending on if it's domain or range. And it's possible that we don't have a smallest value, or it's possible we don't have a largest value. It's possible that our graph would be going forever in the negative direction, which means instead of a smallest value here, we could have a negative infinity. So a negative infinity could go here, or some smallest value. And the same thing here, we might not have a largest value, we might have a graph that goes forever in the positive direction. So we could have here a positive infinity or some largest value. Okay, so we have some start and stop, some smallest value and some largest value in our interval. And then those values, or those infinities or negative infinities, those have to be enclosed by either a parenthesis or a bracket. So we could have a parenthesis, or we could have a bracket here, and the same on the side. This could be a bracket, or it could be a parenthesis, and you can have combinations. So you can have parentheses on both sides, brackets on both sides. It could be parenthesis bracket or bracket parenthesis. So any combination of those closures or in the beginning or the end. Okay, so we're gonna have to distinguish between when do we use a bracket, when do we use a parenthesis, and maybe but the brackets, what those are for, those brackets are to include values. So brackets include values. Those are values that we want to be part of our set. And parentheses then exclude values. And we would want to exclude values if maybe we saw like an open circle on a graph, or we had a maybe something called an asymptote, and we'll talk about those more later, but some kind of restriction in the graph where the graph couldn't go there, the function wasn't defined there, we might have to exclude that value from our domain or our range. And then included values are typically going to be included points. They're going to be like normal points on a graph. So included values we're going to see with closed points on the graph. Excluded values would be something with open circles or asymptotes in the graph. And now infinity or negative infinity, they're treated the same way. They aren't actual values. Infinity and negative infinity are places the graph will approach. And so since they're really a concept and not a value, they can never be included in a set. Okay? They can never be included in a domain or range because they're concepts, they aren't actual values, which means if we start with a negative infinity or we end with a positive infinity, those infinities will always get parentheses. See, these are always excluded, and they always get parentheses. Okay? Alright, so what I'm going to do is read some descriptions here. So let's say we were reading a graph and we could see that the graph, or the domain for the graph, included all x values less than 2. A number line graph would be like a snapshot of what we would see on an actual graph. So if we were reading an actual graph and we saw that the x values were all those less than 2, what would it look like? So I don't know if you remember making a number line graph. But our number line graph, we'd have our value of 2, and then above it would be an open or a closed circle. In this case, since we want all the values less than 2, that means we don't want to include the 2, and we would show that with an open circle. And then all the values less means we would draw an arrow that goes to the left, because that's where all the values less would be. Okay? So that's a snapshot of what we would see on an actual graph. That's a number line graph. So how would we then write that domain in set notation or in interval notation? So in set notation, it's pretty simple. All the values less than 2, we would say all the x's are less than 2. Okay? Now the interval is where do those x values start and stop. So these are x values. Let's read from left to right. Well, how far to the left are these x values going to go? Well, they're going to go on forever in the negative direction, which means this interval is going to start with a negative infinity. Okay, and then how far to the right do the values go? Well, they stop right here at positive 2. So our interval is going to go from negative infinity to positive 2. Now, infinities, we said, will always get parentheses. And then the 2, we have to decide if we want to include or exclude. Well, since we just want the values less than 2, right, since we see that open circle above the 2, we don't want to be equal to the 2, or it can't be equal to the 2, we just want the stuff less. We don't want to include the 2, and we say that with a parenthesis. Okay, that parenthesis means we can get as close to the 2 as possible, but we can't actually include the 2. Okay? How about if we had all values less than or equal to 4? So this is going to be pretty similar. All values less than or equal to 4. So 4 on our number line. And less than or equal to means we can actually include the 4, and we would do that with a closed circle. And less than would still be all the numbers to the left of. So this time, our x's are all less than or equal to 4. So now we have a closed circle there, and we have the equal to on our inequality. And the interval, how far to the left are these values going to go? They're going to go forever toward negative infinity. And then how far to the right are they going to go? Well, they're going to stop here at positive 4. Okay, infinities, parentheses. The positive 4 this time is a number that we can equal. That means we want to include it in our set. So we're going to put a bracket on the 4 to say we can be 4 and everything less. Okay? So we want to distinguish between when we can equal and when we can't using the parenthesis and then the bracket. Alright? Next one, what if we were reading our graph and we could see that it included all x values greater than 1? All x values greater than 1. So greater than 1 means we can't actually include the 1. We would see an open circle on our graph, and then everything greater would be everything right of. So this would be all x values greater than 1. So this time, going left to right, the farthest left value we have is 1. So this time the interval is going to start at 1. And then how far to the right are we going to go? Well, this is going to go to the right forever toward positive infinity. Infinities get parentheses. And since we don't want to be equal to the 1, we don't want to include it, we're going to keep a parenthesis on it. And I don't like that that one's so much bigger than the other one. There we go. Okay? How about all values greater than 5 inclusive? So greater than 5 inclusive means we want to include the 5. So greater than 5 inclusive. Include the 5 and everything greater. So now we have all x's greater than or equal to 5. So this interval is going to start at 5, and it's going to go forever toward positive infinity. So left to right, we're going from 5 to positive infinity. Infinity gets a parenthesis, but this time we can equal the 5, so we say that with a bracket. Okay? Next one is the tricky one, because we've got two things happening at the same time. So if we wanted all values between negative 4 and 7, the number line graph is not so bad. Between negative 4 and 7, so we're going to put negative 4 and 7 here. If we're between negative 4 and 7, that means we don't want to actually equal negative 4 or 7. All we want to include is the numbers in between. So that's a snapshot of what we might see on an actual graph. In this case, the interval is pretty simple. The interval is where do the values start, where do they stop. So we're going to say this interval goes from negative 4 up to positive 7. And since we can't equal either one, we put parentheses on both. Now, the inequality is the tough part here, because there are two things happening at the same time. Not only to capture those x values between negative 4 and 7, the x values have to be less than 4, and they also have to be, or less than 7, excuse me, and they also have to be greater than negative 4. So let me sidetrack with you for a second. So here, again, from negative 4 to 7, we want to be, x's have to be less than 7, right? And they also have to be, those x's have to be greater than a negative 4. Well, instead of saying the two inequalities separately like this, what we want to do is combine them into one compound inequality. So how this is written, let me move this for a second, is if we want our x's to be between negative 4 and 7, then we're going to put x in our compound, this is a double inequality, right in between the negative 4 and the 7. And this part is going to look the same, okay? We want these x's to be less than 7, and then we also want them to be greater than negative 4, but notice here the x and the negative 4 are not in the same place as they are here, so we're going to flip this inequality. To say that x is greater than negative 4 is the same thing as saying negative 4 is less than x. So we need this to be a less than symbol here. So negative 4 is less than x means x is greater than negative 4.
So this is our compound inequality that says the x's are between -4 and 7, where we're less than 7 and bigger than -4. And then if we happened to, let's say, include this, we'd put an equal here, and if we wanted to include this, then we would put an equal here. And we could have a combination of those, okay? So here, we're going to have our compound inequality. These x's are between -4 and 7, so we put x between -4 and 7. We are less than 7, and we are greater than -4. Okay, that's the tricky one. Next one, it's actually reverse, where the set is pretty easy and the interval can be a little tricky. So in the next one, we want all x values except for -3. So what we might see on a graph is a hole. Okay, let's say we have a hole in our graph at -3. It can't be -3, but we can be everything else. That means everything less is okay, and everything more is okay. We just can't be -3. Now, we can't say that with an inequality. I mean, technically we can, but we can say this a little more succinctly than using inequalities or compound inequalities. All x's except -3 can be said like this. X cannot equal -3, okay? So that's a little easier than having to do a compound inequality. Now the interval is where it gets tricky. So if I said how far to the left and how far to the right is this graph going to go, you might say, well, it goes from -infinity to +infinity. But if we say that that is our interval, that means everything from -infinity to +infinity is included. But we can't include that -3, we have to exclude it. So what we have to do is make two separate intervals for this particular case. We have the set of numbers that is less than -3, and we have the set of numbers that is bigger than -3. So we have two intervals. This interval, which goes from -infinity to -3, and we're going to keep a parenthesis to exclude it. And then we have the second interval, which is everything after, everything from -3 to +infinity. And we combine these using what we call a union symbol. So it could be these values, or it could be these values, is what that says. Okay, so we want everything from -infinity to -3 united with, which is just our symbol for or, everything from 3 to +infinity. So this is a union symbol. Okay, it just means or. It could be the set of numbers before -3, or it could be the set of numbers after -3. Whoops. Well, I don't know what just happened there. Taking you to my photo album. Okay, so there's that. And my page does not want to move. There we go. Let me get rid of this. Okay, so now that we have a little bit of practice writing the set and the interval, let's look at some actual cases where we have to identify our domain and our range. So, did I mess anything up here? Sure did. I had my eraser on, that's why my page wouldn't move. Guys. Okay, here we go. So here's some examples. Let's just try to identify the range, or the domain, excuse me, from these examples. So when we're looking for the domain, remember these are the x values. So we're going to use the x-axis as the guide. So we're going to go left to right with these. And I really do like to use the x-axis as the guide. So I'm going to find the leftmost point on my graph. So the first one, I can see the leftmost point is here, but I'm going to take that point to my x-axis. So this is where my domain is going to start. That's my leftmost point. And then I go to the rightmost point. Well, this arrow here means that this is going to be going forever this way. Okay? So my domain is from this point and then forever toward +infinity. So that is where my x values start and stop. That is left to right. So I could say this domain starts at, this is -1, and it goes forever, which is toward +infinity. And because that's a normal closed point, endpoint there, we want to include that -1. Or, if we wanted to use an inequality, we would say that these x's are all either greater than, equal to, or less than equal to -1. Well, we can see they're greater, they're going right of. So these are going to be greater than or equal to -1. Okay? All right, let's try this again. So leftmost to rightmost. Well, if I tried to take this graph all the way to the left, well, at the same time that this graph is going up, it's also headed to the left. So it's going to be going left forever. And then the rightmost point is here, which corresponds with this x value. So if I just highlight it here, I can see the interval for my domain. So left to right, we're going to be going from negative infinity, and then we're going to be stopping here at positive 1. So this domain goes from negative infinity to positive 1. Infinities get parentheses, and this was, let me just double check, yep, this was a normal closed point there. That means we want to include the 1. Or, with an inequality, we could say these x's are all less than or equal to positive 1. Okay? Now looking at number 3. See the arrows on both ends here? So this arrow means at the same time that this graph is going up, it's also headed to the left. It's going to go left forever. And this arrow, again, it's going up, but it's also going right forever. So we're going to go left forever, and we're going to go right forever. And there are no, in the middle, there's no holes or anything weird, no breaks happening in between. Which means this domain is everything from negative infinity to positive infinity. So this domain is everything from negative infinity to positive infinity. Now I can't use an inequality to describe that, but I don't have to. There's another way to describe that set of numbers. It's not the set of x's less than or equal to 1, for example. This is the set of all real numbers. There's no restriction on what goes on in there. So, or we could say all real numbers using our symbol for all real numbers. Okay, all real numbers. That capital R is our symbol for all real numbers. Okay? So that is a domain. Now range is going to function the same way, but instead of going left to right, we're going to go from the lowest to the highest. Okay? So lowest to highest. So I'm going to go from my lowest y value here, and I'm going to take it to my y-axis now because we're dealing with range. These are, again, y values. We're going to go from the bottom to the top. So there's my lowest y value, and notice that's an open point there. And this is my highest y value, and that's a closed point there. So this is my range. From start to stop, bottom to top, is going to be from negative 2 here to positive 2 here. So we can say that this range goes from negative 2 to positive 2. And since negative 2 is open, it's going to get a parenthesis, and positive 2 is closed, it gets a bracket. Okay, or these y values are all between negative 2 and 2. So I'm going to put y in between negative 2 and 2. And we have to be less than or equal to the positive 2 and greater than the negative 2. Okay? Alright. Next. Lowest to highest. So this arrow, although it looks like it's going left, is also going down. So this graph is going to go down forever. This arrow, at the same time that it goes to the right, is also going up forever. So, we're going down forever, we're going up forever. So up and down forever. What am I doing here? I'm trying to get fancy with my colors. Up and down forever, but unlike the parabola, so remember over here, we were going left and right forever and there was nothing weird happening in the middle. This one is going to go up and down forever, but in the middle here, we have something weird happening right here, that hole in the graph. Okay, that hole in the graph means we have to exclude something from our domain, or in this case, our range. So this hole in the graph means that this y value has to be excluded. Okay, everything above that is totally fine, and everything below that is totally fine, but this y value of positive 1 has to be excluded. Okay, everything above, everything below is fine. So this domain has two intervals. The interval below 1, which is everything from negative infinity to 1, and everything after 1, everything from 1 to positive infinity. That interval before or that interval after, those are included in our range. Range, and I put domain. Okay, or we could say, quite simply, these y values cannot equal positive 1. Okay? Alright, the next one here is one of those, what I call U-tries. If you want to pause the video and give it a shot, you're welcome to. Otherwise, let's see, the lowest y value happens right here. And then since this graph is going up forever, right, using the y-axis as the guide, our range will go up forever. So our range is going to start down here at -2, and it's going to go up forever toward positive infinity. Just make sure that when you're reading this, you're not going to go infinity to -2. Okay, it's got to be bottom to top, lowest to highest. So this range goes from -2, that's the lowest, to positive infinity, that's the highest. And since -2 is a normal closed point, we can include the -2 with a bracket. Or we could say all these y values are greater than or equal to -2. Okay? Hopefully this is all looking familiar to you. If not, then hopefully this was a good review. All right, now there are certain functions where, just like yesterday, where we were looking at the different situations to determine if we had a function, we should be able to look at different situations and determine what our domain or range would be. Now here we want to focus just on domain, just because this is a little more conceptual for us in this beginning. If I asked you to find the domain of these equations, these are all functions, if I asked you to find the domain for these without being given the graph, what could we do? Well, we do have a tool that graphs for us, right? So if I wanted to, for example, in number 6, just type in here y equals x, then we have the graph and we can see what's happening. Well, what's happening is that graph is going to go up and down forever. But I would argue that you don't really need that picture to know that answer. So when we're looking for domain, remember domain, these are x values. Okay, we're looking for x's. Think about if we're trying to find all the x values for which this function is defined, instead of actually trying to find all the x values that work, think about x values that wouldn't work. Is there any x value that you would not be able to plug in here that would not produce a y value back out? Positives, negatives, zeros, fractions, decimals, no matter what you plug in here, right? If you put 4 in here, you're going to get a 4 back. If you put -5 in, you're going to get a -5 back. No matter what you plug in for x, an output will be produced, which means all x's are defined, which is why we saw a linear graph that went left and right forever. So if you're trying to find the domain without the graph, you could produce the graph, but you can also just try to think about the restrictions, possible restrictions. What can you not plug in? Okay, think about restrictions and then exclude those if there are restrictions. And I'll show you with the next one in just a second. Okay, no restrictions on this first one though. So this domain is going to be everything from -infinity to infinity. Or we could say it's all real numbers. Okay, the graph goes up and down forever because I can plug whatever I want in there for x and it's going to produce a y value. Now is that going to be true for number 7? Well, let's look at the picture. You're going to see something weird happen if you don't already know what's going to happen. We have 1 over x. And we have these branches of a graph, but notice there's some weird stuff happening around the origin. That's because there's a restriction here. Do we know what's restricted with fractions? What can we not put in the bottom of the fraction? 0 can't go in the bottom of the fraction. You can't have a fraction over 0. Division by 0 is not possible. It's not defined, which is why we had weird stuff happening in that graph. So here, x can't be 0 because 1 over 0 isn't defined, right? X cannot be 0, right? 0 in denominator is undefined. It's a restriction. So for this domain, and you can see this on the picture, everything after 0 is okay, everything before 0 is okay, but around 0 there, we've got no graph, okay? So this domain could be everything but 0. everything before 0 and everything after 0 would be fine, right? X just cannot be 0. Okay. Let me scooch this over. Alright, how about number 8? Again, I can look at the picture. Let's go ahead and take a little cheat. Y equals the square root of x. Do I have a graph that goes left and right forever? No, we have a graph that's got an endpoint there. It's kind of stuck at the origin. Well, why is that? Well, with a square root, isn't there a restriction? Are there certain numbers that we cannot square root? Yeah, negative numbers, right? Can't square root anything negative. The smallest number we can square root is 0. That's why we see this graph that starts at 0, and then everything else that's positive is totally fine. So we can only square root square root 0 and positive numbers. And that's why this domain has to be from 0 and then everything else to positive infinity. And we could square root 0, so we can include the 0, and anything else that's bigger is fine. So we could say these x's that we plug into this function, they have to be greater than or equal to 0. That's the smallest number that we can take the square root of and have something produced back out for y. And that's why we saw a graph that started at 0 and went left forever. Okay? Now how about number 9? And we can look at this picture. We actually saw this one earlier. Y equals x squared. This is a quadratic. This is a parabola. I don't know if I mentioned that word to you yet, but it's going up forever, but at the same time these ends are going up, they're also going left and right forever. So this graph goes left and right forever, which means this domain is everything, because there's no restriction on what I can plug in here. If I put 0 or negative or positive or decimals or fractions, no matter what I plug in for x, I can square it and get a result back out for y. So since there's no restriction, no restrictions on what I can plug in for x, and I really should have said that for number 6 as well, no restrictions, this domain can be everything from negative infinity to positive infinity. And we could also say all real numbers. And that's really going to be true for all polynomial functions. So what I mean is x to the first, or x to the second, or x to the third, or x to the fourth, any of those polynomials, because it doesn't matter what you plug in for x, you can raise it to any power you want, and then it's going to produce a y value. So anytime you graph those polynomial functions, you'll see graphs that go left and right forever without restriction. Okay? How about an absolute value? I'm not going to cheat and look at the picture this time. Is there any restriction on what numbers we can take the absolute value of? Can you take the absolute value of a negative? Yep, you get a positive. Can you take the absolute value of 0? Yep, you get 0. Can you take the absolute value of a positive? Yep, you get a positive. Okay, this is again unrestricted here. There are no restrictions on what kinds of numbers I can take the absolute value of. And so we have again a domain that's going to be everything from negative infinity to positive infinity, or all real numbers. Now just in case you don't believe me, if I was to graph y equals the absolute value of x, we're going to see a graph that goes left and right forever without restriction. Okay? And then this last one is the cube root. I don't know how familiar you are with the cube root, but much like the square root, we're looking for what number, like the square root of 25, right? What number squared makes 25. If I wanted, let's say, the cube root of 8, I'd be looking for what number cubed makes 8. So square roots can't be negative, but cube roots, they can be. If we look at the cube root function, so let me just show you the square root again, right? Square root of x, smallest number we can square root is 0, so the graph starts at 0 and then goes forever to the right. But the cube root of x, and you don't see it on the screen here, so if you go to functions, and then let's go to miscellaneous, toward the middle here we see the nth root, so if I put that on the screen, then I can make the cube root of x another function. Now the red one started at 0, went forever, but what happens with the blue one is we have a graph that's going left and right forever. The cube root is unrestricted. I can take the cube root of any kind of number. I can take the cube root of, let's say, -8, for example, and get a -2. Or I could take the cube root of +8 and get a +2. Or I can cube root 0 and get 0. There's no restriction on what I can cube root, and that's why we see a graph that goes left and right forever. No matter what I plug in for x, it's going to produce a y. So again, this one has no restrictions. And so we see an infinite domain. Everything from -infinity to +infinity, or all real numbers included. Okay? So I know it's pretty conceptual. We're going to hit some of these types of functions more thoroughly in some specific chapters. So this is really just conceptual for now. Hopefully it's making a little bit of sense. I don't want you to get too hung up on it, though, if you're struggling with it a little. Just do your best in the practice, but as always, if you need some help, just reach out. Alright guys, take care.